Hi, my name is Reggie Digilormo, and I teach 9th grade physical science at Airline High School. The lesson we're presenting today focuses on mechanical waves. Students will meet the day's objective by completing various tasks and answering higher order thinking questions at each lab station. You'll see students grouped by ability based on pretest scores taken earlier in the unit. Each station is differentiated by modality to appeal to students' different learning styles. My students and I are really excited to present to you today's lesson on waves. So, good morning, y'all. Today's lesson, we're talking about waves and energy. And so what I want you to do is I want you to take a moment and interpret this quote. We're going to do a think, pair, share today. I want you to copy the quote down on your designated opener box on the sheet. Okay? Then for about 1 minute, and I'm going to time y'all, I want you to think about this quote. I want you to write your interpretation of this quote and what it means in relation to what we've talked about a little bit about waves. Okay? Then after that minute is up, you're going to talk about your interpretation with your partner. Okay? You may begin. Students will start the day's lesson by using the Kagan strategy to think, pair, share. They will first read a quote, analyze it, and think about how the quote relates to the day's lesson. Then they will pair up, analyze the quote together, and then they will share their response with their class. Okay, in 10 seconds we're going to talk and discuss it with our partner. About 10 seconds. Okay, so for the next 3 minutes, I want you to discuss with your partner what your thoughts are about this quote and how it relates to today's lesson.
I think the quote means this is the motion, and you said it means life.
No, like, it's a quote. I think it means, like, waves going through water or something. Seeming a metaphor or something. I don't know.
Got about a minute
I
left.
say the lesson because the water isn't the wave, like I said. It makes up the water. The wave doesn't, how do I say this? I don't know. The water doesn't make the wave, the wave makes the water move. You know what I'm saying? And what do you think?
Well, it will be because we're thinking about it, like the way it moves and all that.
So I'm going to pick a couple of y'all at random to tell me about what your interpretation was. Let's see. All right, Tyler.
We came up with the water is showing us there was a disturbance. The water isn't the wave. The water shows us that there was a wave.
Okay. All right. Does anybody agree or disagree with that statement? Or come up with a different? Okay. Would you like to add to that statement?
Sure. What me and William were saying was, as it says, the wave is not the water, but the water merely told us the wave, how the wave is moving. It's like it's telling us, was it a big wave, was it a little wave, was it a long or short wave? So,
Okay. If it was a large wave, what do you think it was doing? If it was a large wave, what is that showing? A large wave. A large disturbance. And how are large disturbances created, Christian?
By force that was put upon the water.
How are large waves? How are large? You said it's created by a large.
Disturbance in the water.
That's right. And what do waves carry? Does anybody remember? Travanti? Energy. So is it really representing the water? When you read the quote, it says, the wave is not the water. The wave merely told us about the wave moving by. Well, what did it tell us about? Charvon? The energy, right? The energy of it moving by. Okay? So very good, very good. So what we're going to do today and the objectives of today is you will be able to, by the end of the lab today, our goals are to compare and contrast the motion of a longitudinal, compressional is another way of saying it, and transverse wave. You will measure and calculate wave speed, and you will analyze the relationship between wavelength and frequency using measured data from tuning forks of different pitches. So let's go ahead and turn from our opener to our lab instructions. Okay? And keep in mind, as we talk about these things and as you go from station to station, I want you to keep in mind of these objectives that we're trying to meet today. And I'll keep them on the TV screen for y'all. Okay? I also want you to keep in mind, before we leave today, I want you to tell me what your favorite lab station was. So, I'm going to place you in groups. Deshaun, Reagan, Brandon, and William, you're at station 2. Okay? Faith, Charmonti, Trayvon, and Ian, you're at station 3. Yeah, go ahead and go. Bring your packets and pencils with you. Tristan, LaShanta, LaDavius, and Alex, you're at station 4. Stephen, Camille, Haley, Christian, you're at station 5. Daniel, Mo, Dakota, you're at station 6. Michaela, Chloe, you're at station 7. I might change them. A couple rules I want you to keep in mind as you are going through the lab is you're going to review the instructions for successful completion. There's instructions on your sheet and on the laminated sheet on your table to remind you what you're doing. Okay? You're going to work cooperatively in your group. And by doing that, your goal is to provide insight, input, and feedback at every station. Okay? Your goal is to talk or say something to your partners at every single station you're at. Okay? So I want you to kind of get started reading your instructions, get settled in. Y'all can start answering. I'm going to get y'all this music. Yes. Does it go in the same direction of propagation? Or is it parallel or perpendicular to the direction it's going? Okay, so let's make the disturbance and see what happens. Are you ready to time it? Okay, so on your cue, we're going to see how long it takes for this wave to travel down and back. Ready? Go. Let's try that one more time.
Let's try that one more time.
Okay. Don't grip it so tight. Okay. Do we see the different waves, the different peaks of the different waves?
They go from at least sort of big to really small.
What about the distance between peak to peak here?
They're not.
Are they different? Is the distance between peak to peak changing?
Yes.
Yeah. Let's look at it. Let's measure it. Here's a peak. Here's a peak. Peak to peak. Yeah. Let's look over here. Y'all scoot over so you can see. Let's look at the distance in wavelength. What's getting small? The height of the wave or the wavelength? Tell me why.
Because as it goes, the wavelength gets smaller because the sound is dying.
I want you to think of the wave like this. Look at it. It's going up and down, up and down, up and down here. Does it get closer together?
Oh no, they don't.
Maybe let's try this. Let's try to test this one more time. You can hit it a little bit harder, okay?
Okay.
I don't see that. I see them being exactly the same.
I'm trying not to let go of it, so I'm trying to get on the harder grip.
Ready? And what you're going to predict. So we talked about in our quote earlier today.
Stretch the slinky down the floor about 8 meters, 24 tiles. I think we already did that. Send a compression longitudinal wave down a slinky by disturbing it at one end by swiftly pushing it and forward. Describe what you observed. Create a picture. The disturbance with labels to enhance your description. So basically, all we did was pulled it back a little. So basically, all we're gonna do is think of what I think of is like a gigantic rubber band, and if you pull it back and let go, it moves back and forth.
Okay.
Half a second.
Half a second, very good. Okay, so it took half a second for it to travel all the way down and back. Okay. So how are we going to calculate wave speed? You're given the distance, which is how long?
8 meters or 24.
8 meters. It went 8 meters, but it went down and
Back.
so how much?
16.
16 meters. So we're going to copy what we were given. We know that it went 16 meters. Were we also given the time?
Yes.
You found it, right? What was the time, Dakota? Okay, half a second, right? So we're going to write down what's given. Now, are we going to use wavelength and frequency to find the answer to this question? We are? What were we given?
Oh, wait, hang
The
on.
distance and time. So we're going to calculate speed, kind of like, you know how miles per hour, that represents speed, right? And miles is a value for distance per hour, that's a value for time. So we're going to calculate velocity the same way, except we're not going to use miles, right? We're using what? Meters as our source, okay? So we're going to do it the same, we're going to use the same idea though. Okay, so we're going to do the math in that
So
next
it's going to be velocity equals distance distance multiplied by time.
multiply? Think about this. When we say mile, when you calculate speed, do you say miles times hours? What do you say, miles
Per hour.
So per means you're going to do what?
Divide.
Okay. So Dakota, how are you going to set up this equation? So V, equals, and then what are you given? You already know. Which is what? D. What is the value for distance? 16. 16. 16 what? Donuts? Meters. Very good. 16 meters. Divided by what? That's right. 0.5. What again? Hours?
No,
Seconds. Very good. Seconds. And then you can plug that in your calculator if you would like, or you can do that when you divide something by half. It's the same as multiplying it by what? 2, right?
So it would be. No. 16.
Uh-huh. 32. Okay. 32 what? What units do we use for this?
Velocity use.
What did you start with? Your first unit was what?
Distance.
Which was in what units?
Meters.
Meters. So meters per, what was your unit for time? Seconds. So what's your unit for this?
Meters per second.
Meters per second. Very good. Directional wave, right? So longitudinal.
Time and split. 24 times.
Right, Haley can be our timer too. Which one do you think is okay. All right, so how are we going to create this compressional wave? How are you going to create it?
Push forward.
Okay, push forward, or you can do what to the spring? Compress it, right? You create a compressional wave by compressing it. So let's first see what it looks like, what it's going to do. Okay? So all it did is it created a compression that goes down and back, and behind it, what happens to the springs as you compress it? What happens to these springs right here that are right next to it? What do? They stretch, right? It's a series of compressions and refractions, refraction being the stretch of that. All right, so Haley, are you ready to time this one? All right, will you tell him when he's ready to go? Okay. How long did it take for it to go? 0.29? That was a really fast one, right? Okay, so let's go ahead and copy our data down and calculate the velocity of that compressional wave. When do you see most of that water getting disturbed? What sounds are you hearing when the water beats? Okay, beats, because it's creating what? What kind of frequency? Yeah, a frequency. What kind? Low or high frequency? High frequency? What kind of pitches do high frequencies have? What do we think?
I don't know.
Do you think they create really big waves, like big long waves, or do you think they make really short tight waves? Big long waves. So if they have a big long wave, what kind of frequency are they going to have? A low frequency. These are low frequency waves, but they are creating more disturbances, right? You can see in there. Okay. Now, what do you think is going to be? You can go stop. What do you think is going to happen with the classical music?
I don't think it's gonna move at all.
You think there's gonna be more? And she thinks there's not gonna be much at all. Why do you think there's gonna be more?
Because like how the instruments are high.
High pitch, so you think they're gonna create more of a disturbance, okay? Do you agree with that, Ian?
I think the first one
Has less, and so does Charvanti. So we're gonna see in this case, okay, what happens. So go ahead and you can search for it. Where do you see more disturbances there? Did it just get, I saw disturbances, did you? Did it just get louder or softer when you saw it? Louder. It got louder, right? Because loud means it carries more what? Energy. It carries more energy, right? The louder I get, the more energy I'm giving out. A more sound wave, more energy I'm giving those sound waves to make them travel. So it's going to create more of a disturbance, right?
An object vibrates at its natural frequency by absorbing energy from a sound wave of the same frequency. So,
It's not like speed.
vibrates natural. Yeah, it does. Is that one on here?
Speed.
Probably. Speed. Yeah, so number 19 is rate speed.
What are you going to do here to create this transverse sound wave? Are you going to create it the same way you did the compressional wave? You're going to do, so you're going to pull, you're going to create a disturbance in the direction it's going? Or is it going to be, Christian, do you think it's going to be in the same direction? Do you think it's going to be parallel or perpendicular to the direction the wave is traveling? What's the difference between parallel and perpendicular? Okay. Okay, so let's see how we're going to make that disturbance by going perpendicular to the wave's propagation. So you're going to pull it which direction? Down. Alright? So what did that look different than the compressional wave? Okay, it appeared differently. What do y'all predict is going to happen to the speed of this? You think it's going to be a little bit slower. Alright, so you get ready, and you're going to pull it down and get ready, and you're going to measure the time it takes to go down and back. Okay? What was the difference in time? Was it longer? Did it take longer? Yes, it took longer. Okay. Why'd you circle the gamma rays and put a box around the radio waves for number one?
Well, the frequency on this one is greater than this one. And
Okay.
the wavelength, like this, is greater on the delta.
Okay. If you think about it, it's nice and long, right? So if you just had this box traveling through the whole time, pretend those aren't there. Would you get more wavelengths going through a certain period of time, or would you get less compared to these? Would you have way more of these travel through an area?
In a box?
Yeah, if you put this in the box and you put this in the box, which one would have more wavelengths travel through it? The one with shorter wavelengths, or the one with longer? The shorter ones, right? So what does that mean for its frequency?
The frequency is like higher, the wavelength is lower. If the wavelength is higher, the frequency is lower.
Very good, very good. Very good, I would agree with that statement.
have probably seen a stone thrown into a pond. The energy from the initial impact of the stone on the water creates waves which can be seen traveling outward from the center. As the energy moves outward, the molecules of the water collide with each other like a chain reaction. Waves like this which require matter.
The second
I'm giving you a little bit extra time with these stations. Okay, let's go back, clean up our station. After the lab, students will return to their desk and play a game called Plickers. This is a way for me to assess the students' level of understanding of the objectives. Okay, so you can't trade cards with the person. Alright, so some of y'all, when you got to that point in your lab, when you hit the tuning fork against it, okay, and some of them are louder than the other, okay? Some of them are louder than the other. And what did that do to the amplitude? It says to find amplitude, measure what? How would we find amplitude? What will we be measuring? Keep them up, held up. I need to see everybody's held up. Whatever answer you think, keep them held up nice and high. Does it require more or less force for that wave to be really large? More force, okay? But how will we measure that wave, how high up it is? How do we measure, Tyler?
From the rest position to the trough. Or the
Okay.
crest.
So you're saying that the correct answer is what for this one? D. And why did you? Because it's from the rest position to how far it goes down, or from the rest position to how far it goes up. Let me ask you this. If it had low amplitude, it was really, really quiet. If it had low amplitude and it was really, really quiet, do you think it would get really, really high and really, really low? Or do you think it would stay closer to the rest position?
Stay close to the rest position.
Okay, because it has less what? Amplitude, or because it has less energy to give it that amplitude, right? Very good. Next question. All right. It says the figure, not to the right below it, okay, shows wave movement during 1 second. So from here to here, it travels this far in 1 second, okay? How are we going to calculate the frequency of this wave? I want you to think on that. Why'd you pick A?
There's like two things on the 2 links. So I just thought it was
So 2 wavelengths went through in how many seconds?
like 1.
1 second. How do we measure frequency? We count the number of wavelengths over the time it takes, right? And how long did it take for those wavelengths to go through?
1 second.
1 second in that case. So your answer is what? A, 2 what? Why didn't you use 2 meters per second?
Because that's how we're measuring.
Right, we're measuring what? We're trying to find the what? The what? The frequency. When would we use meters per second, though? What was that, Tyler? Use your voice.
To find how fast.
How fast, the wave velocity, right? Very good. All right, so last thing we're going to do today, okay, y'all can go ahead and pass your Plickers cards forwards. All right? And before you leave today, what I want you to do is the exit ticket on there. All right, so you'll see 3 different things on your exit slip. What I want you to do is I want you to tell me first, what station was your favorite station of the lab today? Okay? What station was your favorite station of the lab today? Okay? And you can go back, you can go through, you've got your lab packet right there. And you can see what station you kind of like best when you go back and read that. Okay? So what, in the second box, you're going to tell me why is this important to know. Okay? So what, why is it important to know? And for the what about tomorrow, the third box, questions you may still have in regards to that. Okay? All right? I want you to take a minute, and what you wrote down, I want you to share it with your partner, and then we're going to share it with the class. So we're just going to spend a minute kind of sharing with your partner what you learned.
I learned about the frequency. When it's higher, the wavelength it's lower. About the high pitch and low pitch.
Well, I said Station 1 was my favorite lab. What I learned was the difference between the personal wave and transverse wave, yeah.
What was your favorite station? Yeah.
Oh, my favorite station is the station that, you know, when we did the music thing. And
Okay, the
thing.
music station. Why did you pick that as your favorite station?
I picked it because, like, it was cool when I, like, to see the different shapes it made when the frequency got a lot higher and lower.
Okay, and so what did you learn there?
I learned that when the frequency is higher, the wave is more compressed or more close together.
Okay, and so Why is that important to know?
I don't know.
You don't know? What kind of pitch did it create?
A high pitch.
A higher pitch. Okay. So that might be important to know. Do you like to sing? Does anybody like to sing in here? Think about frequency. Okay. If you want to make sure, you can check and make sure you're in tune, and you can measure frequency. Okay. You can see your frequency and make sure you're staying at that same match the pitch. Okay. That's what people use tuning forks for, right? They try to match the pitch of those tuning forks. Okay. Is there any questions you still have about that? One question I might have is, what would happen if I changed the shape of a tuning fork? Okay, something like that. Instead of it being the way it looks, kind of like a pitchfork, right? If we change the shape or size, something that you might have. Okay? Anybody else have something they want to share? Tyler, you got something?
My question,
Yeah? Okay, so
how far, like, what would happen if a wave just, how far would it need to go to stop, and what would happen if it does stop?
okay. So what happened, why do waves stop moving is your question with that. What was your favorite station? Let's just put this all together. What was your favorite station today? Station 1, and why, what about it? What did you learn about it?
See just how compressional waves compress and where it's at.
Good. And so why is this important to know?
So you can distinguish a compressional wave and a transverse wave.
Oh, okay. Very good. I like that. And so your question again for tomorrow is what?
It was how far can waves travel before stopping?
Okay.
But like, why do they stop? Because it isn't a wave energy.
Mm-hmm.
So wouldn't it just be transferred into different
Maybe.
energy?
Maybe that energy is transferred to something else because we know the law of energy conservation, right?
Energy cannot be destroyed or created.
That's right. So where does the energy go, right? You have to think, where does the energy go? So that's a very good question because we know we have to follow that law. Very good. Daniel, you had something to add to that?
I'm just going to ask a question.
Uh-huh.
Actually, I do have a question. What happens when the two waves crash into each other?
You want to know what happens when two waves crash into each other. Okay? We call that interference, and it depends. And we'll talk more about that. That's a good question to keep for tomorrow. Okay? That's where we talk about interference, where they're two colliding waves. You see them collide together. They're interfering.
Like if it's, I was wondering if it's like a sound wave, does it just like create kind of like a boom sound?
So you think it might build it up? It might increase its, what?
Amplitude?
Amplitude. Okay? Depending on the situation, it does. And depending on, so we have this thing called constructive interference that we'll talk about, and destructive interference. If they meet each other at certain ways, in certain phases is what we call them, they either build each other up or break each other down. And that's something to lead into tomorrow. So that's a very good question, y'all. All right, good job today. Very good. So what I want you to do at the very bottom of it is I want you to tell me of the objectives, okay? I want you to pick an objective that matched the station that you picked as your favorite. Our objectives for today were to compare and contrast the motion of a longitudinal or compressional, that's another way of saying it, in transverse wave. You'll measure and calculate wave speed. Okay? I will analyze the relationship between wavelength and frequency using measured data from tuning forks of different pitches. I want you to tell me on the back of that exit slip of your favorite lab station which one you hit today. Alright? Good job today, y'all. Y'all hand them to me on your way out. Good job. Have a good day. See you tomorrow. See you tomorrow. Thank you for watching the video. It's been my pleasure to represent Airline High School and the amazing faculty and staff that's here. I hope you enjoyed the lesson.